It's okay. Okay, great. So, welcome to Stochastic Methods 2. I'll try to figure out a way to make this more comfortable. I took a photograph as evidence that this is overcrowded. So, my name is Sean Mine, and I think did most of you get a message from me today? Okay, good. Yeah, I've been on the road. I was on sabbatical last year, and having a great time in in Berkeley and Stanford and NREL and Paris and all sorts of things. And my graduate student Aditya was actually there. He's going to be a teaching assistant for the course, sort of a supervised teacher. And this guy is amazing. I mean, he's a resource, so talk to him. So this course, I mean, as some of you have heard me talk about similar topics before, it's very dear to my heart. And I feel, whenever I teach this course or related courses, I always reflect back, do I really need to cover the abstract nonsense? So I put the crazy symbols over there. Can you see them at all? Yeah. I mean, and and I know I do. And Aditya, you agree, right? It's sort of the language, as I said in an email, to go to any conference in these areas. I mean, you can't understand a word of what people are saying at these information theory conferences or machine learning or control, signal processing, unless you have this language. But it takes some time to adjust to it. But for example, a random variable is a function, and we all agree with that. When we say random variable in a lecture, we all agree that's a function from this abstract set omega to maybe the real numbers. It might be complex. I mean, random variables can take on values in abstract spaces, but we'll stick to reals for now. So that's just language you've got to memorize. In last lecture, one of your fellow students actually gave a crash course on the projection theorem. I think we got the hours confused. I think that we thought there was 2 hours instead of 1, so maybe it was a bit rushed. But yeah, do we have one more chair? Any way you could hunt for a chair? Okay. So let's think about this. So last lecture, maybe I'll review a bit of this, but there's this space L2 of y1 through yn. I'll remind you what that is. It's equal to the set of all functions g of y1 ... yn. I should give this a name. The set of all random variables z, which are functions of y1 through yn, and z is in L2. Remember what that means. That means that z is a random variable itself, and it's square integrable. You can square it and it's integrable. All right. So basically, what are we saying here? This is a approximation problem. In applications, y1 through yn are observations, and when we do this minimization, we're really minimizing over all functions of the observations. So probabilists are brave. Who would think of trying to come up with a function, to approximate based on all, minimizing over all functions from Rn to R. Normally when you think of optimization, you're thinking about optimizing over R5. Or maybe, Google likes to brag about optimizing over a million-dimensional parameter space to train a neural network. This is infinite dimensional, and you're trying to solve an optimization problem. And what are the applications? Well, it used to be, a decade ago, it wasn't machine learning that everybody was obsessed with, or maybe before the financial crisis, everyone would get into finance. And so I'd always say, well, this is like Wall Street, and X X would be a value of stocks tomorrow. And since it's just a scalar, it's just one stock, which is pretty silly. Right. And what would be the YNs? You tell me. So tomorrow I'd like to estimate the value of my stock, my favorite stock tomorrow, this one. I mean, of course, it'd be really a portfolio. What would you say the observations?
The value of stocks. The closing price.
So let's stick to that one. So it could be the prices over past week. This is fun. I'm so glad you said that. You look at these stocks here, and this is like n plus 1, and this would be my x that I don't know the value of. And if you're taking a baby statistics course, you'd say, linear regression. Need another colored pen. And you'd say, linear regression. There it is. There's x hat, That'd be pretty stupid. There's a million reasons why that's stupid. Because first of all, it's like I had some great examples over there. What is it again? It's like Brexit vote. Right? The Brexit vote. I mean, right now, that's an observation. And there's Trump's tweet. But not just one. You'd have to look at the history and how they're connected. I mean, it's incredible. Is he going to pull out of Syria or not? And is this stock related to, some military company or not? I mean, this, an arms. I mean, it's so insane. So, like any kind of notion of linear regression like that is almost never, is never what you're thinking about. That point of view in this course is barely going to even appear. You have a bunch of data, and you'd like to estimate some partially observed quantity. Given some observations here. Now, of course, they're brave, but they're also stupid because you can't solve this problem, and that's why you have all these methods for function approximation. And I mean, I'll start and you'll finish. There's neural networks. There's kernel methods. There's, oh my God, yes. There's, wow. The thing is that don't give up. Just search for a chair. Oh damn! I think we're down to one pen. Wait, where did it go there? So clustering. So basically, give up on trying to get a point, an estimate of, say, a conditional mean like this. Oh, by the way, that is the conditional expectation, right? Was that mentioned last time? That's for something that's square integrable. That's the definition of the expectation of x given y1, the yn. But so instead of a conditional expectation, it's actually a bit stronger and weaker to say, is the stock high or low or in the middle? Just break it up into 3 levels and come up with some sort of estimator like that. And there's reinforcement learning when you have dynamics. I mean, that's a way of trying to solve these infinite dimensional problems. Oh, really? Did you find a chair somewhere?
That's fine, actually.
Yeah.
No, it's Fine, I will.
Okay.
You show.
Yeah. But so all these sort of hacks are designed because we can't solve these problems exactly. And of course, there's other problems. Like here, this is not, reinforcement learning is not about trying to solve a conditional mean. A conditional mean is just part of it. But conditional means a part of the problem. And of course, also, a conditional mean is not nearly enough information. You know, the mean is 10% higher than it is today, but the spread is so huge, I have no idea, and I might be very risk averse. And so I'd like to know the conditional variance as well, given my observations. All that, I'd like to maybe know also, maybe I'd like the third moment. Maybe I'd like to get some idea of exponential moments, given my observations. And so all sorts of techniques to try to approximate this. But it's nice to have the gold standard. You know, I mean, for a conditional mean or conditional variance, being able to say, I would love to have the actual optimal nonlinear predictor for the mean, covariance, and so forth. How can I best approximate it in some parameterized class, say? All right. And so this course is supposed to give you the tools to do that, you know. And so when I say it like that, it's all of machine learning, you know. It's like just everything, and all of information theory, because all information theory is about taking data and trying to find out what's underneath the surface. You know, what was being sent or what was being hidden, and how I can you know, how can I hide information so it's hard to solve these problems. Yeah. So that's why it's it's an incredibly important course, and so and the abstractions are worth it. Again, I've been teaching this course for 25 years, and every time I've taught it, I think, is there any way to get past the abstractions and just do it? And it would be an incredible disservice to avoid the foundations. We wouldn't understand each other, you know. Like every time I try to talk about anything, I'd have to say, well, this is x random variable. It has a density, and it has a joint density with these other random variables, but it doesn't really. I'm just saying that so I can talk to you. And then I talk about a limit. Does a limit have a density? What is it? You know, I mean, it has a distribution of some sort. And what does it mean that they're all random variables? I mean, I've been talking about, a joint density for three-dimensional random vector. Now I've got a sequence and its limit. How would I talk about that just in terms of densities and mass functions? I couldn't do it. The language would become impossible. Okay, so this is, thank you, Kolmogorov. He came up with this beautiful foundation that makes the language very nice. You just have to learn it. Yeah. Okay, cool. So today I want to basically review all of chapter 1 in a way of Bruce Hayek's text. So basically the basic axioms of probability and examples and consequences of the definitions. And so, yes.
Is it necessary that y1 to yn have to be part of L2?
Good point. Yes, thank you. Good question. So, what's really nice, when everything's square integrable, you can just say the definition of conditional expectation is a minimum norm problem. Done. It's so sweet, Suppose that, were you asking, do the y's have to be in L2? Of course not, because I could always make them bounded. I could always just convert them and keep the same information. So L2, oh damn, my last, wait, I have to read next door. So actually, one of my servants, would you like to? Ah, man, you get an A, you get an A. Wow, they deny, this is really nice. This would be a good exercise. Well, it's pretty obvious, but. So I like being slowed down at this point in the course, so please ask questions like that. So imagine I basically make my observations bounded by just looking at some function. Instead of my measurements, I look at some function of the measurements, right? And I made two assumptions. I assumed it's invertible. Well, three assumptions. Bounded range. If it's bounded, it's square integrable. Okay, so the motivation's clear. Invertible, why would I assume invertibility? Should be clear?
No 2 points map to the same point.
Well, that's the definition of invertibility, but I don't want to lose information, is what you mean, yeah. I basically,
It's still only a function.
yeah, well, it's just that I said that L2 was all functions of the data. Any function of y1 through yn can also be expressed as a function of phi of yn, phi of y1 up to phi of yn under invertibility, okay? So I don't lose any information by assuming invertibility. And why did I assume continuity? I didn't need to, but. What?
Ease?
No, well, ease an explanation. I didn't want to say the word Borel. I want these guys to be random variables, And so a continuous function of a random variable is a random variable. Okay, so that's the reason. So yes, it's immediate that I don't have to assume that the observation's in L2. I also don't have to assume that X is in L2, but then that's really much harder. So let's just forget about that. Let's just let you take a measure course. Let's just take this as a definition and forget about functions that aren't square integrable. If it comes up, then we'll worry about it then. But I don't think it'll come up. So that's a perfectly good definition. And it coincides with your naive definition of conditional expectation. I mean, but basically through Bayes' rule and all of that. But I'm not going to. Maybe we'll talk about that later, or maybe in the homework. This definition is projections, exactly the same as you'd get if you defined a conditional density, and all of that. There's no difference whatsoever. So cool. That's a great question. So let me just say a few. Let's just play around with this, a little bit, to review what hopefully you saw in a course before, and to practice with the definitions. But I want you to just always chant before you go to bed. Random variables are not random. They're just a function from some abstract set omega to the real numbers maybe, or maybe complex. It might be a complex random variable. There's no such thing as randomness. There's just uncertainty. Randomness doesn't exist, and this is a model of something. And the thing is, we don't know omega. Capital Omega is some massive thing up there in the heavens, and we don't have access to it. We only can see functions of this abstract creature in the sky. This is as close as parabolicists come to talking about God. Is this omega in the sky? All right. So recall the axioms. So, again, so these aren't axioms yet, just the words. So omega is a set of, just a set. Now here's the weirdest thing in the world, is that God picks a little omega, and he or she did that at the beginning of time, and then omega has been with us ever since. Okay? Everything in the world is a function of that little omega that was picked. In the most abstract setting, that's what happens. So if you go to, a course on stochastic differential equations, or something where you really talk about stochastic processes, this thing has no meaning at all except for little omegas, and that omega is fixed once, and it models the past and the future, everything. That's what I mean. That's the joke about it being like God picked omega, and that's the strange thing about it. It's so abstract that omega doesn't have time visible in it, even though it's modeling all of time, future and past. So F is a collection of subsets. So we can ask questions about omega. You know, we can say, you know, is omega in A? And A might be the event that the stock is half its value tomorrow, you know. That's something, you know, that's a function of this little omega, but we don't know. We haven't seen tomorrow yet. There's a whole bunch of properties we're going to impose, which I'll review in a moment. And P okay, so the point of defining this collection of subsets, you know, subsets of omega, is because we have to define this probability measure on sets, and it turns out you can't define them in all subsets of omega. There's some really deep theory that says it's sometimes impossible to you know, and I'll give you an example in a moment. I can't give it in full detail. You have to take a measure theory course for that, but I can say something about it. So we define a class of subsets of A for which this probability measure is defined. Right? And these here are the three properties, the Kolmogorov's axioms. Here are the three for F.
Dr.
Yes.
That 0 to 1, right? That's a closed interval on the set to 0 to 1.
Yeah. This is just the you know. Yeah. So P of A is less than or equal to 1 and greater than or equal to 0 for any A. Yeah. Okay. That's what I mean. So that's what I mean by it takes on real values anywhere between 0 and 1. All right. And so the three axioms of Kolmogorov are, first of all, capital omega is in F. Okay? So the set omega is something happened, and that is something for which I can define P of A, I assume. And the second one is that it's preserved into complements. Right? And the third one's the one that's most important, is that if I have a sequence of events, so I have an infinite sequence of events, so now there's a subset of F, then the union is also an F. All right, and so you really need that. So if you really want to bore yourself, you can learn about what happens if you restrict this assumption to only finite unions, and a lot of things go wrong. So those are the three axioms, and in line with those are parallel assumptions on this probability measure. And what are those? So this is redundant. You know, I just told you that P is I just told you that P of A is between 0 and 1 for any for any A. So I've already told you that. I'm just making it formal now. If these guys here are mutually exclusive, what I'm about to say here. So if I've got a bunch of events which are mutually exclusive, I know that their union, I've just said the union is an F, so I can define P of the union. And you all know the answer. It's a sum. And lastly, probably the whole thing is 1. Okay, so it's incredible that you take these 6 little axioms, and then you get to the central limit theorem and diffusion approximations for queuing networks in heavy traffic, and you get all this crazy theory that developed just overnight after some just ridiculous abstractions. It's really, I mean, it's amazing. It really is one of the most amazing branches of applied mathematics. It's really something. So it looks like these are the axioms. This is just an anecdote, right? So, why didn't I put in my axioms that P of A is less than or equal to 1? It's not said.
A complement also belongs to.
Yes. So, so omega is equal to A union A complement. That's right. So that's what you said. That's what you have in mind. And so 1 is equal to the probability of omega, which is equal to, there's a disjoint union, so it's a sum. And we just said the probability of A complement and probability of A are both non-negative, so that is greater than or equal to probability of A. So, you can deduce all sorts of silly things from these three building blocks. All right. And much more. The empty set should be here somewhere. Is the empty set, I said that the whole set is an F. But if A is an F, then so is its complement. So the empty set is equal to all of omega complement, which must be an F. So, that's another thing you can say. All right? Okay. All right. So, Neil on Tuesday went through and gave the example people always go through, which is coin flips. And I'll go through some other examples. Like basically, let me put it this way. Most of the time, you are not going to think about what omega is. Nobody's going to ask you to construct what omega is. You're going to be, you have some random variables. There are dysfunctions on omega. It's some abstract thing. You never have to worry about what it is. But you can sometimes construct capital omega, if you feel like you have to, and it may be useful to do that, even though no one ever does. I don't know. That's one thing that does confuse me. Why in every book on stochastic processes you go about constructing omega when there's no reason to at all. But I'll just follow the canon and do that. Yeah, I mean, there's one setting where it's important. And it's important because you have to motivate. Why on earth are we constructing F? Okay, but I will go back to that example of the head toss. Okay, so I just flip a coin once, and omega of the set of outcomes. If we really wanted to find the minimal omega, we could take omega what do I want to say here? I know this is stupid, but I just want to make sure there's nothing else I want to say. Now, you know, okay, you would never do this again. You would never say, I'm interested in a couple of coin flips, and then I'm going to go through and construct my capital omega. That's not done. I'm just giving an example. All right, now F. Well, we know it has to contain omega. That's one of the axioms. And so there, and also we know because of the axioms it has to contain the empty set. You know, I could stop there. Why wouldn't I stop there? This satisfies all the axioms. I could put a closed bracket there.
You can build any interesting events.
Yes. I want to know what's the probability of a heads, and my probability measure is defined on events. If I only had 2 events, I know the probability of something happening is 1, and the probability of nothing happening is 0, and I wouldn't have much information. So you throw in everything. All right. So when you have these discrete models, it's typical just to take omega to be, take F to be the set of all subsets, and everything's fine, you know. And that's why there's no point in doing it. I mean, it's just a waste of time. And that's that. But what's really more interesting, and this is actually example from the book. This is example 1.1.1. I don't think you'll read much more there. There's another example. 1.1.2 is that you start off with just saying, what if omega is equal to, say, this interval? You know, so there's a set of t and r such that 0 is less than equal to t, less than equal to 1. Just in case that's not clear. So when I write this, I mean the set of all real numbers between 0 and 1. You know, this is where you really get into trouble, because you'd like to do the same thing that's done here. You'd like to say that F is a set of all subsets, right? But it turns out you couldn't even define the uniform distribution if you did that, you know. So if you took the set of all subsets, you wouldn't be able to extend the uniform distribution to all sets. And that's really tough, you know. I mean, I remember I took that as a senior undergraduate. I was a math major at UCLA, and I remember that was tough. And I haven't reviewed it since. Okay, so now it's just faith-based. I just trust it. But there's, for F. Here's the sort of the procedure. You would like it to contain all intervals. I got less than. Okay, so you'd like it to contain all open intervals, all right? Now there are lots of sigma algebras that could contain all intervals. It would take, a few days to prove that. Maybe it's not a few days, I don't remember, but it would take some muscle to show there is at least one. I forgot to say this, F is called a sigma algebra. When you hear sigma algebra or sigma field, it means the same thing. And all that means is that those axioms hold. That F contains, omega, it's closed under complements, and it's closed under unions. So when those properties hold, it's called a sigma algebra or sigma field. So it turns out, lots of sigma algebras that contain every interval. Yes?
So when you, going back to the first example.
Yeah.
Sorry to chase back, but why isn't H union T in the...
Oh, because H union T is already omega.
Okay.
Yeah. H union T is, that's it. And it turns out also, I'm doing this all in words, if you take an arbitrary collection of sigma algebras and take the intersection, that's also a sigma algebra. So if you what we call the Borel field, or the Borel sigma algebra, again, there's so many people use so many different terms. It's a Borel sigma algebra, the Borel sigma field, the Borel field, it's equal to, I'm never going to do this again, the intersection of all G such that G is a sigma algebra and G contains all the intervals. All these intervals, right? Now, that's why, you'd have to take a measure theory course to make this, this is not hard to prove, that the arbitrary intersection of sigma algebras is a sigma algebra. There's only 3 things to check. Every one of these guys contains omega. Check, the first axiom holds. It's completely trivial to show that this is a sigma algebra. But the hard part is to show there's just one. There exists one sigma algebra that contains all the intervals. That takes a bit of muscle. Okay, but this is when you say the smallest sigma algebra containing the open intervals, that's what we mean, because it's the intersection of all of them. So when I say smallest, I really just mean the intersection. All right, that's just the same language. That's the definition for sets. That's what we mean by smallest, is the intersection of them all. This is just language. Okay, so this is a measure theory course. I'm just going to take it for granted it exists, and that is a typical thing you'll assume. And then an example of P.